Okay, so this part mentioned about the frustrated total internal reflection. Of course, the total internal reflection you should have learned it in high school, but you may not know what is the frustrated total internal reflection. 这个沮丧的全反射。Okay, so here it says a 45-90 degree stream. Okay, 就是那种棱镜嘛，就是will deflect the beam of the light by total internal reflection. Okay, so if it is incident by 45 degree, okay, we only have total internal reflection. So here we have these two, of these streams. Okay, so if we place it apart, okay, so we have a large gap in between. All the light will be totally reflected. Okay, so this is the incident way, and then this is the reflected way. Okay, all of the way are totally total internal reflected. Okay, and here we go to the right case first. Okay, if we place these two streams touching each other, which means that there is no gap in between, then all the light will go through. There will be no light to be reflected. Okay, all the light will go through because you have merged the two interface together. However, the interesting thing is, if we place these two streams close but with a small gap, okay, here we have a small gap. Okay, so the interesting thing is that there will be something reflected. But part of it can go through. It is something similar to the tunneling effect in the quantum mechanics. Yeah, it's something like if we can provide a potential wall there. Okay, so if it is a particle or maybe a photon, if it has a energy, smaller than the potential. Of course, the potential for this gap is large. Because it should originally be totally reflected. Yeah, the potential here should be large. But if this gap is small enough, yeah, of course, the probability for this particle or the photon to go through is actually exponentially decaying. Okay, so it becomes small. So only small part of the light can go through this gap. Okay, but actually some of it can go through, and then yeah, there will be light going through this system, and then this is called the frustrated total internal reflection, because you expect it to be totally reflected, but if this gap is small enough, part of it can go through. That's why we call it frustrated. Yeah, if you would like to know more, you may try to check it out on this link. I'm not sure whether this link still works, but yeah, you may try. Okay, so here shows a table for the reflection indices. Okay, some indices for the reflection. Okay, so as I mentioned, for the vacuum, it should be exactly 1. It should be exactly 1 because this one is just like n equals c over c, so it is always 1. Okay, but for the air, it is only slightly larger than 1, so 1.00029. Okay, so usually when we consider the air, it is very similar to the vacuum for the EM wave characteristic. And then for the water, 1.33. Okay, for the yeah, so in high school you should have seen it for the optical system. And for the let's see, glasses, typical crown glasses, 1.5. And then let's see, yeah, for the quartz, 10 yin, 1.46. And then here, yeah, for the diamond, yeah, you can see, lady should know, should like the diamond. Okay, so for the diamond, the reflection indices is 2.42, so it has quite a lot of total internal reflection. Okay, so if the refraction index is larger, then there will be more probability to make the total internal reflection happens. Okay, so actually the diamond, why it's like very shiny, because it has a large reflection index. Okay, so here, this is a way to generate the polarization light using the reflection rather than the filter. Okay, so so it says a ray of unpolarized light. Okay, so actually this one is the unpolarized light. Okay, so it used the green arrow and the yellow dot or the orange dot, okay, to represent the E field has two direction. Okay, in maybe let's say this is x-axis. Okay, so in y-axis and z-axis it has the E field component. Okay, so it is unpolarized light. Okay, so it says if a ray of unpolarized light in the air is incident on a glass or maybe other material, is also okay. So the angle will be different. Okay, at the Brewster angle. Okay, so this is very important. It's the Brewster angle. So the electric field along that way have been resolved into components perpendicular to the page. Okay, so the idea is that here the incident ray is at the Brewster angle. Is at the this is the Brewster angle. Okay, so for the reflected ray, this is partially polarized. Not totally polarized, only partially polarized. However, this is totally polarized. Okay, you can see only the orange dot here. There is no green arrow along this reflected way. So we can actually generate the polarized light using the Brewster angle. And of course, part of the energy goes to here. So only part of the energy of the yellow dot goes to here. So which means that, yeah, the energy for the green arrow is stronger than the yellow dot. Okay, along this refracted way. So this is partially polarized. Okay, so yeah, so the reflected light consists of an original component parallel to the page and a weaker component perpendicular to the page. This light is partially polarized. Okay, so here tells you what is the Brewster angle, how to calculate it out. So the Brewster angle, theta b, is arctangent n2 over n1. Here we know that n1 is air, with a smaller refraction index. Here we assume that n1 is smaller than n2. So here we have n2 over n1. n2 over n1 is larger than 1. So which means that arctangent of n2 over n1 is larger than pi over 4, 大于45度. Okay, so this is the equation to calculate the Brewster angle. Okay, so actually here we have an interesting property. So here, as we know, this is refraction. Okay, which means that the incident angle and the refraction angle is the same. So this is theta b, this is also theta b. The interesting thing is that here we draw it as a right angle. So it means that the reflected way is always perpendicular to the refracted way. Okay, theta b plus theta r is 90 degree, which means that this is also 90 degree because this whole angle is 180. So theta b plus theta r is 90 degree. So let's try to derive it out. Okay, yeah, I don't have it on my notes, so let me try to derive it myself. Okay, so here we should have n1, sorry. No. Okay, quite. This is okay. So n1 sine of theta 1 equals n2 sine of theta 2. Also, we have phi 1 is actually theta 1 is actually theta b. It's actually theta b. And also, we have theta b equals arctangent of n2 over n1, right? n2 over n1. Theta b is arctangent n2 over n1. Okay, so here we would like to find, this is theta 2. Theta 2 here, we call it theta r. Okay, so this is actually theta r. So let me try to rewrite it as a n1 sine of theta b equals n2 sine of theta r. Here we would like to prove is theta b plus theta r equals 90 degree or pi over 2. Okay, so here for theta b is actually like this. So here we can draw it as a theta b, and then this is actually n2, this is n1. So this is square root of n1 square plus n2 square. Okay, this is theta b. Okay, so we would like to find theta r. Theta r will be n1 over n2 times, okay, let's draw it like a sine of theta r should be n1 over n2 times sine of theta b. Sine of theta b. So here, sine of theta b is actually n2 over this square root of n1 square plus n2 square. So it is actually n1 over n2 times n2 over square root of n1 square plus n2 square. Okay, so here we can actually cancel n2. So it becomes n1 over square root of n1 square plus n2 square. Okay, so n1 over square root of n1 square plus n2 square is actually cosine of theta b. So which means that we have sine of theta r equals cosine of theta b. And of course, theta r, theta b are between 90 degree and 0 degree. So actually we can just try to convert it like cosine of theta b is actually sine of pi over 2 minus theta b. Okay, so actually both of them are between 0 and 90 degree, which means that the argument should be the same. So here we should have a theta r equals pi over 2 minus theta b. And then we move it over, so it turns out to be theta b plus theta r to be pi over 2 or 90 degree. So actually the reflected way and the refracted way are always perpendicular to each other. Okay, so here we have two additional examples to finish off this chapter. So the first one is also about the polarizing filter. So it says that unpolarized light is sent into a system of three polarizing sheet. The angle theta 1, theta 2, theta 3. Okay, theta 1, theta 2, theta 3 are measured counterclockwise from the positive direction of the y-axis. They are not shown to scale. Angle 1, 3 are fixed, but theta 2 can be varied. Okay, so the intensity of the light emerges from the sheet 3 as a function of theta 2. Okay, so this one cannot move. This one cannot move either. Only the middle one can move, can rotate. Okay, so so what percentage of the light initially intensity is transmitted by the system when theta 2 is 30 degree? It asks you what is the intensity when it is theta 2 is 30 degree. Of course, for the first step, we should determine what is theta 1 and theta 3 first. So the clue is that if theta 2 is 0 degree, 90 degree, or 180 degree, the intensity will be 0. I will be 0 when theta 2 equals 0 degree, 90 degree, or 180 degree. So that which means that theta 1, theta 3, one of it should be 0 degree, one of it should be 90 degree. Because you can imagine, if one of it is 0 degree, one of it is 90 degree, then if the middle one is also 0 degree, then between these two should be 90 degree. Cosine of 90 degree will be 0. So there will be no way to go through. And if it is 0 degree and 180 degree is actually the same. Okay, so we just ignore it. For the 90 degree, between these two, okay, it's a 90 degree. So there's no way to go through. So which means that theta 1 and theta 3 should be 0 degree and 90 degree because I equals 0 at 0 degree, 90 degree, and 180 degree. And then we can say without loss of generality, 就是不是一般性, we assume theta 1 to be 0 degree, theta 3 to be 90 degree. Okay. So which means that if you don't believe, you can try to assume theta 1 to be 90 degree, theta 3 to be 0 degree. You will get exactly the same answer. You will get exactly the same answer because we only need to know what is the intensity when theta 2 is what is the intensity of the output when theta 2 is 30 degree. Okay. So without loss of generality, we just assume theta 1 to be 0 degree, theta 3 to be 90 degree. Okay, so in that case, we can actually calculate. This is I0, this is I1, this is I2, and then finally I out. Okay, originally I0 is unpolarized, so I1 is nothing but 1/2 of I0. And then for I2, theta 2 is 30 degree, theta 1 is 0 degree. So we should have I1 and then cosine of 30 degree. So which is nothing but 1/2 I0 times square root of 3 over 2 and then quantity squared. And then for I out should be something like I2 cosine of 60 degree. So which is nothing but 1/2 I0 square root of 2 over 3 square times 1/2 quantity square. So this is actually the same answer, which is like 9.4%, 0.994 IO. Or actually it is like 0.094 IO. So which means that I out over IO should be 9.4%. Only 9.4% of the light can go through. Okay, so next one is about the uncertainty of the wave. Okay, so it says a certain helium neon laser, okay, high night laser, okay, emits red light in the narrow band of wavelength center at 632.8 nanometer. Okay, so this is a wavelength, and with a wavelength width of what is wavelength width? So, and a wavelength width of 0.01 nanometer. And then it asks you what is the corresponding frequency width for the emission. Actually, this is somehow related to the quantum mechanics about the Heisenberg uncertainty principle, Heisenberg 测不准原理. Okay, so the idea here is that of course, when you talk about the EM wave, okay, you will give it a specific frequency or specific angular frequency, the omega. Okay, let's say here this is actually the lambda, and then this is actually, we call it delta lambda. So as I mentioned, C should be F lambda in the vacuum. So this is a speed of light in the vacuum. And then this is the frequency times the wavelength. So if we already know this is the lambda, we can actually determine the frequency. Actually, we can determine the frequency. So if this wavelength is accurate, no error, no any error, then this frequency will also be accurate. Okay, we can just plug in the number, or this is, let's say, 3 times 10 to the 8th power, or if you want to make it more accurate, 2.998 times 10 to the 8th power. Okay, so and then you plug in lambda to be 632.8 times 10 to the negative 9th power, and then you can really calculate the frequency of this laser beam. Okay, actually it tells you that it has a wavelength width. It has a wavelength width, which means that the wavelength is not accurate enough. Yes, the wavelength is not accurate enough. Yeah, if you just try to draw the x-axis to be the wavelength lambda. Suppose this is the lambda. Okay, you would expect this should be something called the delta function. Okay, so which means that all the laser should have this wavelength. But actually, in the real world, it can't be that perfect. In the real world, it should be something like this. Okay, it should have something like a normal distribution. A normal distribution. 常态分布. Okay, so which makes it even though the frequency or the wavelength is concentric around this lambda, but there should be a width. There should be a width here. So we call it the delta lambda, or maybe you just specify half of it. But actually we have a delta lambda here. So that okay, the wavelength is not that accurate. Some of it is 632.8 nanometer, but some of it may be 632.8, maybe plus half of it, or maybe minus half of it. Okay, so maybe there is a small deviation, Okay, so which makes also for the frequency, if it is a delta function, it should also be a delta function, but unfortunately it's a normal distribution. So in that case, in the frequency domain, we also have this shape. Okay, so a point, if it is here, it should correspond to this point. If we have a longer wavelength, it should refer to a lower frequency. If we have a shorter wavelength, it should refer to a higher frequency. Okay, so for all of this, you can just calculate. Okay, just like flip it, because f and lambda are inversely proportional to each other. C is a constant. So if we have a smaller wavelength, we have a higher frequency. If we have a longer wavelength, we should have a lower frequency. Okay, so that's the idea. So here the delta lambda is actually the width of this normal distribution. Of course, this normal distribution will extend to infinite far away, but here we try to find, if this is the peak, this is the peak. We try to find, this is the half of the peak, and then we see, how width it is, and this is actually the delta lambda. So similarly, this is the peak, and then this will be the delta f. Okay, so this question try to ask you what is the frequency width. What is the frequency width? Actually, we can do it two ways. For the simpler way, you can just try to calculate. This is, let's say, this is lambda, and then you try to plus half of lambda, plus a half of lambda, and then you plug in this value, and then you can try to find this point. And then also you can just try to have lambda minus half of the delta lambda. You get this point, and then you plug in this equation, you can get that point, and then you subtract them, then you can get delta f. But here, as a bachelor student, we can use the calculus to calculate it. Okay, so here we have C equals f lambda, which means that we have a f equals C over lambda. C is a constant. F and lambda are variables. So which means that we try to take the differential of this one. So this is variable. This is also variable. So we should have df equals C, and then lambda, 1 over lambda. 1 over lambda means lambda to the -1 power. So take the derivative, it becomes negative lambda square, and then d lambda. Okay. Or if you don't familiar with it, you can just imagine, this is something like f of lambda equals c over lambda. So you can take df d lambda to be negative c over lambda square, and then you just move this one over, and then you will get the same thing. So actually what we really need is this one, because suppose this delta lambda is small or delta f is small, we can just imagine this delta lambda is this d lambda, this delta f is this df. Okay, so we can just plug in this value, and actually we can just take the absolute value. Take the absolute value here. So delta f is like c over lambda square, and then delta lambda. Okay, we just replace that df to be delta f, d lambda to be delta lambda, but we just take the absolute value because we have a negative sign. It means that if we have a larger wavelength, we have a smaller frequency, so that from here to here is go from left to right, from here to here we go from right to left. Okay, so we can just plug in the number. So we have a 3 times 10 to the 8th power over lambda is this one, 362.8 times 10 to negative 9th power, and then times this wavelength width, delta lambda is 0.01 times 10 to negative 9, like this. Okay, so you can really get that delta f is actually 4.79 gigahertz. Okay, 7.49 gigahertz. Okay, the width here. Actually, it seems very large because this is 10 to the 9th power, but actually the frequency here is even higher. You can just try to guess the number. Okay, so f is like c over lambda. F equals c over lambda is like 3 times 10 to the 8th power over lambda is 632 times 10 to negative 9 power. 0.8, we just ignore it. So you can see this is like 10 to the 8th, 10 to the 17th, 10 to the 17th, and this is around 200. So this is around 10 to the 15 power hertz. Okay, so this is around 6 order higher, or at least 5 order higher than that one. And actually, this is really related to the Heisenberg uncertainty principle. Although in high school you may learn the Heisenberg uncertainty principle as something like a delta x delta p is larger than or equal to h bar over 2. But actually, for the frequency and time, we also have the similar thing like delta f delta t is larger than or equal to h bar over 2, something like this. This is the uncertainty of Heisenberg uncertainty principle for the frequency and time. Okay, so if we can measure the frequency with smaller error, then the error for the time will be larger, and vice versa. And similarly here, if we measure the position to be more accurate, then the measure of momentum will have a larger error, something like that. So this is also related. If this delta lambda is smaller, then this delta f will be wider, and if this is larger, and then this one will be narrower. Okay, so this is so actually here we really conclude